Oh, you can't see. Turned off automatically. Fine. That's why you couldn't see. Not so different from the jet lev, maybe, but a bit less controlled, perhaps. And maybe more juvenile, I suppose, as well. So anyway, so interesting things to get. And a whole host of the other Jackass movies, no doubt. Are they still in vogue? I haven't looked at those for an age. We looked at this last time. The prone land speed record, and maybe we'll start off doing that and talk about that. We talked about Air France. Oh, yeah, let's have. Yeah, I don't know. It's another.
Tennessee Williams and Captain Kirk and Bob Elliott.
I thought this was someone else, but apparently another person actually did this. But you'll see in a minute. I remember working up in southern Ontario in 1990 when a guy kayaked off Niagara Falls. And so this is apparently a falls in
Brazil, where this fellow took the express elevator to the basement via kayak. Pedro Olivia rowed his boat a record 127 feet to the bottom of the falls and amazingly survived without a scratch. The drop took exactly 3 seconds. It breaks the old record by about 20 feet, and while it looks like they might have just chucked a dummy over the falls, like in the movie The Fugitive, the stuntman and his friend appeared on the Today Show this morning to verify the story. Mr. Olivier then kayaked off the Prometheus statue into the ice skating rink.
That's a joke, I guess, right? So, yeah, fine. So survive. So what I thought it was a guy called Jesse Sharp kayaking off Niagara Falls. And so they found his boat, but they didn't find him. Niagara Falls is about the same height, I think. It's 100 plus feet, 40 or so meters. Beaten up tip of a boat, looks like a Perception Dancer for those of you who boat and know that. More cowbell, not sure why that's there. Oh yeah, this is kind of interesting. So obviously from what we learned about before, we know that the velocity that you go down, the water goes down, is the same velocity that the guy goes off the boat. You're just falling due to gravity, nothing more than that. And so we'll talk about some more Bernoulli type questions today. And so this is kind of cool. Obviously kind of an interesting use for it, but exactly the same as our jet lev, but instead of using water that's pumped through an umbilical, you're using chemical reaction. I guess it's jet fuel. It's a jet pack of some kind. So you're mixing jet fuel with air and burning it, expanding it. And I guess those would be rather warm. I can't imagine that they wouldn't be warm. And so you can use it to jump around the place. And you get quite high with it by the looks of it. Quite an interesting piece of technology. Big backpack. I guess the backpack is for the fuel. And the actual engines are in your arms. And so that's one use of it. I think there's another use which is more interesting and civilian, and just relies on the fact that for mountain rescue, right? So exactly the same deal, same backpack, hovering, I don't know, 10 feet off the ground. Want to climb up a mountain to go and rescue a climber. As drone in the background taking pictures. And you can just move up the slope very quickly. Same idea, just using burning a fuel, making sure your hands, I guess, don't touch the things, using them individually to nothing more than just your position of those to be able to steer and to be able to keep you off the ground. So just like the jet lev, we could do the calculating with that. The only thing that's different is that now the fluid that is coming out of them is no longer water at 1,000 kilograms a cubic meter. It's air at about 1,000th of that, 1 kilogram. And so you could do the scaling, you realize that you'd have to have a much larger velocity to get the required force on the ground to be able to lift a body, same kind of weight as the jet lev. So kind of interesting applications for these. All right, so that's kind of where we are. So that's the eye candy for today. I think Junpeng has not, I checked this morning, he hasn't posted the grades. He has them, but he will post them soon. So that'll be today, I guess, for better or worse. And so that'll be sometime today, I'm guessing. What did I do? But today, I just want to continue with what we were talking about previously. I guess I should correct something that we did last time. If you remember, we were talking about the jet lev, and we talked about the work needed to, first of all, the flow rate we needed to be able to lift this thing, which was something like a velocity of 14 meters a second. And then we multiplied this, the force, which is the weight that it's holding up, which you could also calculate from the pressure times the area that it impinges on, multiplied by the velocity. So this isn't work, this is actually power, right? Don't need to be pedantic about it, but work is equal to energy, which is equal to force times displacement. So it's in units of Newton meters, which is a joule. And power is the rate of doing work. Which is Newton meters per second, which is joules per second, which are watts. Hence the use of W here. And so instead of a displacement, we're using a displacement rate of velocity, and that gives us the power that you'd need. So this would be the amount of power you'd need to be able to run it. And the other thing we didn't do last time was to do another example, which perhaps we'll do now. We looked at, before we get started, let's go to what we might try and do today and introduce exactly what I want to do today. I just want to do some examples, then that's all I want to do. And so we talked last time about flows normal to streamlines. Rarely do we have to use those. Much more commonly, we use flows along a streamline. This represents a long streamline velocity, upstream and downstream. We can write it downstream and upstream, it doesn't matter. For now, these terms, loss terms, are zero. We don't care about them. And we can write it, I always write it this way. Well, this is just writing it between two places. It stems from the fact that from one upstream to downstream on a streamline, the potential, the Bernoulli potential, if you like, is always the same, comprising a pressure head, a velocity head, and an elevation head. This also is the energy that we put into the system by a pump. Don't care about that now. So we've used Bernoulli a couple of times. I made the point of what it meant, what it requires. It requires inviscid. I don't think I got them all last time. Irrotational. Incompressible. I think I said isothermal. That is the case, but that's not the main one. The other one was steady state. So inviscid means that essentially viscosity is zero. There are no viscous losses. So air comes past me, or water flows in a pipe, there's no drag on the pipe on the water slowing it down. So inviscid is a requirement. Irrotational means that you don't get eddies forming as you flow past the structure. So maybe if you flow past a structure, air comes here and goes around it. You don't get things doing this as it goes past it. Incompressible means it should be a fluid, but actually we'll apply it to compressible fluids. Incompressible means a liquid, but we can apply it to gases, which are compressible. And steady state means it always looks the same. And so, yes?
What causes the eddies to form?
Because, not Coriolis, a small perturbation allows it to get out of whack. Maybe there's some roughness on here that makes it go out from the skin, and that develops that. But I guess they're for larger scale as well. I think just a flow field, the flow field, interacting flow fields. I guess you don't have roughnesses for tornadoes. Tornadoes are from air coming over the Rockies, stuff coming up from the Gulf, gives a twist to it, and that turns it. So the original flows of the air might not be collinear, I suppose, right? They're offset somehow. That's probably a better explanation than roughness. It will come from roughness as well. Okay, so we'll maybe have a look at some of these. We talked about continuity, volume in equals volume out, or mass rate in equals mass rate out, which if we have Bernoulli's equation with 6 unknowns, we have, or with 6 terms, if we have 2 unknowns, we can link the velocities and then only have 1 unknown and 1 equation, then we can do that. And so we can do some examples. So let's just try messing around with some ideas. So the first one is maybe a corollary of the jet lev, but it's going to be the world speed, land speed prone biking record. So you got this guy in a bike, Graham something, Scottish guy, and he's going down the road. Wheel here, a wheel here, and his little face here. And so relative to that, we have a velocity. So we said that it has to be steady state. And so we kind of alluded to it for the pitot tube, right? We know that if you're looking at a bicycle go past you, initially it's here, then it's here, then it's here, if you're taking a picture. So the air in front of you at this particular spot initially has 0 velocity. The bike comes along, it has to get around the bike by doing this, just as we previously drew. And so the air has to be moving some, and then the bike is over here and the air is static again. So that clearly, if we took at those 3 shots, the point of air that we have here is not steady state because it's changing its velocity with time. It's 0, then it's 10 miles an hour, then it's 0. And so what we have to do is choose a frame of reference that we attach ourselves to the bike. So we're traveling with the bike, and so instead of the bike moving, we're looking at a static bike, and the velocity of the air in front of us is moving towards us, and we're static, like a bike in a wind tunnel. And so if we want to do this, then we could do the same as we did before. We can write the pressures at locations 1 and 2. We can write Bernoulli at 1 and 2, and then choose what we know for each of those. Plus V2 squared over 2G. We know that upstream air pressure, atmospheric, elevation Z1 and Z2, they're not 0, but let's make them the same. So we get rid of them if they're physically the right elevation. This is Z, and this is Z. Velocity here at point 1 is 0. We don't know what the... No, not velocity, that's wrong. I just disregarded my own tenet, right? It's coming towards us. It's not equal to 0. That's the whole point of this exercise, I guess, right? So velocity is unknown, the pressure is unknown, but the velocity here of this jet impinging, V1, V2 has to be 0 because it's turning a right angle, so it hits this, this has to be 0. So if we rearrange that then in terms of pressure, we end up with pressure 2 is equal to V1 squared over 2g times rho g, which is equal to rho V1 squared over 2. And so if we know what the terms are for that, and if we know what this area is, area, I don't know, 1 meter squared, let's try that. Then what do we have? Force is going to equal to pressure times area. Pressure is equal to density of air times V1. What's V1? It was 60 miles an hour, which I happen to know is 30 meters a second. So this is 30 meters a second squared divided by 2, which is P, times 1 meter squared. So how good am I? 3 is 9, which is essentially 10 plus 2 zeros, which is 1,000, is that right? 1 times 3 threes are 9, 10, 2 zeros, 100,000. Is am I missing something? Density, velocity squared, density, velocity squared over 2 times 1. So 1 times 10 to the 3 is, this is half times newtons. And so if we are going, that's the force that's applied. And so if we want to know the work, power, I guess, right? That's right. Equals force times velocity equals 0.5 times 10 to the 3 newtons times 30 meters a second is equal to 15, that's right, kilonewtons per meter per second equals 15 kilojoules per second, which is 15 kilowatts. So the power you need to cycle at that speed is apparently 15 kilowatts. Well, the output, one of the things that I had on here, the output of a person, anyone know what the output of a person at max, was it VOX or VO2 is? Hazard a guess? About half a kilowatt. So I know this probably, if we look at the thing that we had, this is it. I can't imagine the front of this, which is here, is a meter in cross section. So maybe it's a tenth of that, right? If it's this, since it's tapered, so that would take it down to the power would be 1.5 kilowatts. That's probably closer to reality. If we think a max for a person is a kilowatt, then this is pretty close. It's probably because it's tapered, it's actually not a straight, flat face, and so it's probably of the ballpark. So it probably can't be 1.5 kilowatts unless he's a super athlete, but it's something of that order, and that's how you can get that number. Okay? So, spatial reference frame matters. So it has to be steady state. What other examples do we have? Yeah, okay. Well, let's do Jesse Sharp as well, because that's instructive. So you have Niagara Falls. And you have Jesse Sharp wanted to come across Niagara Falls. So you have points 1, 2, 3, and 4 if you wanted to, right? Niagara Falls is about 120 feet, I think. And so what do we want to do? We want to calculate what the two things I guess we want to calculate. We heard that it took 3 seconds to get down. I guess we could try and verify that. And we don't know what the impact velocity was at the depth, but we could write if we want to calculate the velocity. If we had so the velocities we calculate using Bernoulli are always streamline velocities. Doesn't care that we're going around a right-hand angle. It's always a streamline speed, if you like. And so it's always in the direction of the streamline. And so if you wanted to calculate velocity, then we would calculate elevation 1 plus P1 over unit weight plus V1 squared over 2G equals Z3 plus P3 over 2G plus V3 squared over 2G. This isn't 2G, is it? Unit weight. And so what do we know? So if we take our datum here as z equals 0, then Z1 we know. Atmospheric pressure as gauge pressure. Atmospheric pressure before it hits the bottom is gauge pressure. Z3 is 0, just from our datum. And as it comes across here, its velocity downhill is 0. It's starting off at 0 velocity, just like it's emptying out of across the edge. So this term here is 0. And so from that, we can get that V1 is equal to this is 0. What am I doing? I'm not doing very well today.
Are we looking at point 3 or point 2?
Point 3. So yeah, I don't care about point 3. This can be either point 1 or point 2 at the top, right? We don't care. It's easier perhaps if it's point 2 because it becomes more obvious. Clearly this is going at some small speed as it goes along here, but it's not going anything like the speed it goes down here. So if we take it as it rolls off the lip, you empty your cup off the brink of Niagara Falls. Initially, in the cup, it's going at 0 velocity. So if it's going at 0 velocity, then this is 0. But we don't know what this is. So if we want to write that around, I'll go the other way. V squared 3 over 2G is just equal to Z1. And so if we just rearrange that, we get 2G Z1 square root is equal to V3. We've seen this before. It's exactly the same as if we had a container. If I can draw a container.
Did you need to write Z2?
Z1 and Z2 are the same though. Thank you. So it's exactly the same as if we had a container. With a free jet coming out of it. This is H. This is V7, just so we know. Now VZ. V7. The equation for a free jet was that the velocity is equal to 2gh square root. And so all this is exactly the same as this. It starts off at 0 velocity here. This is the same height. It doesn't care that it's doing this. You could also, if you had a ramp, I think I'm going to confuse this diagram. If you had a ramp that instead looked like this, so that the water is flowing down this ramp at some velocity here, so you had V5. What's V5? This, I guess, is V7. V5 is going to be what? It's going to be exactly the same as this expression here. So V5, if we looked at it, would be equal to 2g z2. But importantly, the velocity v5 is oriented in this direction. It's in the streamline. So the one thing you do have to remember for this is always that the velocities that you're talking about are along a streamline. For a free jet, it's vertically downwards. Falling off Niagara Falls, it's vertically downwards. If it happens to be a ramp, a stream flowing down a steep incline, it's along the direction of that incline. And of course, it would have components in the vertical direction and the horizontal direction. And each of those would be different. They'd be the maximum value here along the streamline that you have to worry about. And so that's useful to know. And so we get exactly the same expression as we do for a free jet. And we do, even if it's inclined. It only cares about the height of this drop. And I guess the other thing that you could do if you wanted to prove to yourself is if you want to look at what this acceleration is, if you write the acceleration in the z direction, we know that acceleration is rate of change of velocity with time. And we know that's the same as rate of change of velocity with time multiplied by 1. Right? And if we looked at the change in z with time, this by definition is a velocity. And we look at this, then we could take the derivative of dz of vz times vz. That's just what this expression is. And of course, we have this defined here. So the derivative of this is 2g square root times the derivative of square root 2. So z to the half is minus half to the half, right? Z to the half differentiated is minus a half multiplied by the exponent. And the velocity is just going to be equal to 2g square root, this term here, times z to the half. And if we're good at our math, then square root 2g times these two terms together give us 2g. Square root 2g times square root 2g, and this is just a half z to the minus a half times z to the half. These cancel out. This becomes 1. So the acceleration in the z direction that we get is just g. It's just the same as Jesse Sharp coming over the brink and just falling down, jumping off a building for that matter. It's exactly the same acceleration you'd see if you did that. So we probably didn't need to derive that, but it's perhaps useful to do. Well, I guess actually the other thing that we might be interested to do is how long does it take to come down? Well, we know how to do that. So you've done that in your past before. Velocity is equal to initial velocity plus acceleration times time, right, from statics. So velocity is just equal to change in elevation or change in location with time. And so you could rewrite that as dz is equal to v0 dt plus at dt. And you've seen this before, right, obviously? Right. So if you want to know how long it takes to come down, you could just solve this equation. You know that as it's coming over the lip and going down 40 meters, the velocity here is 0. You know that you have to get down 40 meters. So you know this is 40 meters. And you can, well, because it starts here, the constant drops out, and so it's just 40 is equal to times 2 divided by acceleration, which is gravity, equals t squared. And so we should be able to work out whether that really is it really 3 seconds? So 240 is our 80 divided by 10 square root. Square root of 8 is about 3. Yeah. Square root 9 is about 3, right? So you get how long it takes to come down. Okay. May seem kind of esoteric, but it's actually kind of useful for some of the things that we would do. So, point being, we always use streamline velocity. So, so other questions. So here's another esoteric example. So you have a bucket that has a jet coming out of the bottom of it. You have that jet directed at some angle. How high does it go up, and how far does it go if you're doing that? How do you get that from Bernoulli? We could go through the example. I don't want to. I don't know if you like me writing these things out, but I think it's better to do that. Okay. Let's do the example. All right. So here's the idea. Let's go through it slowly. We have a bucket that has a jet coming out of the bottom of it. That bucket has a water level in it. And that height is, we'll call uppercase H. We have the horizontal. We're going to take this as our Z. Z equals 0 is here. We angle this jet up from the bottom at some angle theta. And we want to know two things potentially. What's this height? And what's this length? I'll do uppercase L. So the easiest way we could do this would be to direct the jet vertically upwards, right? So if we had the tube so that instead of being horizontal, it was going vertically upwards. then how high would the jet get? So we can write point number 1, point number 2, point number 3. So if we want to calculate if it's directed vertically upwards, we could write Bernoulli between those 2 points. P1 Z1 plus P1 over gamma plus V1 squared over 2G equals Z2 plus, no, Z3 plus P3 over unit weight plus V3 squared over 2G. And then figure out what we know. So it's directed vertically upwards. We know that this is equal to H. We know that this is atmospheric, so the pressure has to be 0. We know that this is in the atmosphere somewhere, so this at point 3 also has to be 0. We know that it's a big tank, so the big tank means that this isn't being drawn down, so this velocity is 0. And we know at the peak of the apex, as it goes up, the definition of this point is where the velocity is the vertical velocity is no longer finite, it's 0. Doesn't mean that it's not flowing along the streamline, but the vertical component of the velocity has to be 0 by definition, right? This is the velocity in the streamline. So here's the same thing. Where it stalls out at the top of its travel, this velocity has to be 0, so this has to be 0. So the only way that this equation can make sense is if Z3 is also equal to H, which is exactly what you'd expect. So if you have it going up here, it starts off at some big velocity here. It's acting against gravity as it goes up to slowly slow at this apex where it's 0. And of course, once it's here, a drop of water will fall back down. And when it falls back down, it'll be going exactly the same velocity in the opposite direction as it was when it was up here. As you can imagine, it's symmetrical. So that's one way to get that. And of course, if you just had a pipe that was attached to the side here, the pipe would rise up to this elevation just as a standpipe on the side of a cistern in a toilet, for that matter. So how do we get the magnitude of H? So what we could do is we can define another point, 4. And we could, well, what's the velocity at point 2? So if we want to get the velocity at point 2, we can write this as Z1 plus P1 over gamma plus V1 squared over 2G. It won't change from these from before. And it's equal to Z2 plus P2 over gamma plus V2 squared over 2G. So this is the streamline velocity. So this is the velocity V2. This is still going to be H. This is still going to be 0. This is still going to be 0. This is going to be 0 from the place of our datum. And because it's come out into the fresh air, pressure acting on all sides has to be the same. So this also has to be 0. So it ends up being the equation of a free jet, which is just that V2 is equal to 2G uppercase H square root. You only have this term, and you have this term, and this is what it's going to be. And so, in other words, you could also write this in terms of the original expression here, which will be useful for us later, which is that H is equal to V2 squared over 2G, right? This term and this term are the only two live equations. So what now do we do about this? So if we want to get the height of this, we could write it between these two locations. Seems complicated, but it's not. So we could write now between locations 2 and locations 4. So this would be Z2 plus P2 over gamma plus V2 squared over 2G is equal to Z4, which we don't know, plus P4 over unit weight plus V4 squared over 2G. So what do we know about this system? We have V2 coming out here from this. We know that the horizontal components and the vertical components is going to be V2 cosine alpha, theta rather, and V2 sine theta. And we also know that this velocity here has to be exactly the same as this velocity here, right? It's going horizontally. There's nothing acting on it to slow it down. So the velocity of V4 has to equal V2 cosine theta, right? Newton's first law, third law. A body with nothing acting on it keeps on going. That's all it's saying. And you can think of this as a water drop. And so we can revisit this. We know that this elevation is 0. We know that the pressure is 0. We know that this elevation is what we've called lowercase h. We know that this pressure is 0. And we know that V4 is equal to V2 cosine theta. And we happen to know what V2 is because we have it here. So if we write this expression in terms of V2, we get V2 squared over 2G times 1. This term here is V2 squared cosine theta squared over 2G, right? Just by substituting the fact that we said this, V4 is equal to this. And so we can write this as subtracted off as cosine squared theta, because we have this term, and it's going to be equal to h. And so all we've done is we've said that we know the horizontal velocity of the water coming out here from this geometry. If we know this horizontal velocity, we know it doesn't change as it goes horizontally because nothing's acting on it. So it has to be the same at the apex of its climb and then descent. So if this horizontal component of this jet is equal to V2 cosine theta, it has to be this. We put them equal to this. And if we know that this term here is this, then we can substitute this with just uppercase h. So ultimately, the height is equal to 1 minus cosine squared theta times the original height of the bucket. H is the original height. So it means that it's less than, has to be less than h, because cosine is always positive and finite. And so it just reaches the arc that it climbs to is given by that. So that's one part of the question that we might want to ask. How high does it go? I guess we could also ask, how far does it go? And I guess for that we'd need to know something about its height. And so we kind of know that, right? If we know that it's going from, if we know what the height is, and we know that this equation here, probably the easiest thing to do is write that out. We know that z is equal to v0 times t plus a half a t squared. So if you think about being at the apex of this climb, and the vertical velocity v0 is 0, right? Top of this climb, it stops, stalls out, comes down. And so the vertical velocity by definition has to be 0. And so this is 0. This is gravity. Z is the distance it's going to fall, which we've said is h. And so h is equal to 0 plus a half g t squared. Or the time it takes to fall is going to be equal to 2 times h over gravity, square root. Check my working. You know I always get them wrong. And so we know the height from here. We know gravity, 10 meters a second squared, 9.81. So we have the time, and we could work out what that is. And we know that in going along here, we know that V4 is equal to V2 cosine theta. Right, we've done this before. We know that coming out of this pipe, we know the streamline velocity, and so know the horizontal magnitude is equal to this. And so if we know what V4 is, then the distance traveled, not Z, we call it uppercase L. L is equal to just the time it takes to fall down, which is going to be the time it takes to, the distance traveled is going to be the time it takes to get up there plus the time it takes to get down. So it'll be 2 times the time it takes to fall. And so the distance traveled, L, will be equal to the velocity times time, which will be equal to V4 times 2 times T4, if you like. And so if we know what this time is, then we know this. If we know what V4 is, and V4 is just equal to V2 cosine theta, and V2 was just equal to this. Uh, 2gh square root. Bit complicated, but actually much less complicated than this, by the way, which has a hose coming out, which really complicates it. But the idea is pretty straightforward. So I'll leave it there because I see some people are writing. The idea is pretty straightforward. We can get the velocity it comes out of here. We know it's a streamline velocity along the trajectory that it's directed. If it's directed upwards, it will climb to its apex. The apex will be height of the water in the tank, and it'll go no further. If it's angled, it will go off to the side. If it's angled, we know this velocity along the streamline. If we know the velocity along the streamline, we can also get the horizontal velocity, and we can also get the vertical velocity. If we know the streamline velocity here, we can write Bernoulli between these 2 points. And since we know that this streamline velocity is linked to this along the streamline velocity here through Bernoulli. We can solve Bernoulli to get the fact that the height we solve for is equal to the ratio of these two components of velocities in the horizontal direction, which given by this. Once we know the height, we could calculate the height by thinking of us sitting at the top of this jet and dropping water down to the floor. That's the time it takes for it to fall. The time it takes to fall, if we multiply that time by its horizontal velocity, that's the distance it will go horizontally between its apex and the side. And since it's symmetric, it's a parabola in going across from one to the other, then the length it would travel would be the time taken to fall to go this distance, the time taken to climb to go this distance, so 2 times that is the total distance. We know the water is traveling horizontally at a velocity we know, and so we can calculate all the coordinates. So a bit complicated, but it's just a matter of being able to write these out for streamlines. And it's much, believe it or not, it's much simpler what we've done there than what we would do otherwise. We've always, just close up with one quick example. I know you're maybe drinking out of a fire hose with the rate we're doing this morning. One other free jet example. We made the point before when we talked about a free jet that if we had this, then the velocity at point 2 we could write as a free jet was just equal to V2 is equal to 2g uppercase H square root. This is on a streamline. If the jet was directed downwards, then that would be the same velocity coming out here as it would be going horizontally. And if it was directed upwards, also it would be the same velocity. If it was going upwards, it would climb against gravity, it'd reach an apex and stop and then fall down. If it's going horizontally, it would go, if this was sitting on a table, it would be like the Belgian fountain, the guy peeing in the Belgian fountain. We've always assumed that this cross-sectional area, A1, where we get this magnitude, is always big so that we can throw away this velocity. But if this is not big, and the area that it's flowing here is area A2, if we write Bernoulli, we'd end up with Z1 plus P1 plus V1 squared over 2G is equal to Z2 plus P2 plus V2 squared over 2G. And if we do our usual things to limit our variables, we know that pressures up here are 0. We know that pressure where the jet comes out is also 0. We know if we take our datum here as 0, then we get this is equal to 0. Is that the bathroom? I think it is, actually. And so usually, if it's the big tank approximation, for this, we assume that V1 is equal to 0, and we can get away with that. Big tank, small pipe. If that's not the case, then we might have to write that the velocity in the top of the tank times A1 is equal to the velocity 2 times A2. And the reason we have to do that is because we've got Bernoulli. We have one equation, but we have two unknowns. We don't know velocity 1, and we don't know velocity 2. And so what we need to do is we need to write velocity 1 as a function of velocity 2. And we need to substitute that in here. And if we do that now, our equation's written only in terms of V2. And so, for instance, this example that I'll wind down to is saying if we keep on flowing water in here at some volumetric flow rate Q, so the level always stays at the top of the tank, always stays at level H, what is this flow rate? Well, clearly, we're assuming that this has some kind of small velocity, V1, because we're pouring stuff into the top, so it has to be making room for that new fluid to come in, so it has to have a finite velocity. And so if there's a velocity here and a velocity here, we have one equation with two unknowns. We have to get rid of one of the unknowns. This is our continuity requirement. Conservation of mass, actually, constant of volume. And if we substitute for the velocity 1 as a function of velocity 2, then we only have one unknown. We can solve for V2, and therefore we can solve for flow out of the system. And there's a very long example that does exactly that, which is there. We made it easier because we're talking in terms of areas instead of diameters of the thing. You have to use pi d squared on 4, but you get the same result. And we didn't do that. We can do that next time. Okay. Thank you very much. Questions?